Welcome to our discussion on mixture and uniform motion problems, two of the kind of most commonly used families of word problems. So if you can understand how to recognize a mixture problem in all of its various forms and how to recognize uniform motion problems in all of its various forms, you'll figure out that you can solve all of them in basically the same way, and it makes it a lot easier. You don't have to fear these word problems so much. So of course, those are our two objectives, mixture and uniform motion. Let's start with mixture problems. A mixture problem involves combining two ingredients that have different prices into a single blend, or different, you don't have to always be different prices, just different amounts of a certain characteristic. So, different amounts of cost means different prices. You could also have another typical mixture problem is in chemistry. Take something that is 20% alkaline and mix it with something else that's 50% alkaline to get a total mixture of 5 gallons that's 35% alkaline. Well, you can see now that the different amount of the quality is their percent alkaline, right? Because one had 20% alkaline and one had 50 or whatever the heck I said. But you get the idea that you're mixing two different things that have a different amount of a certain characteristic. Usually it's price or percentage of something. Those are usually the two biggies. We might come across a different example, but just think about adding two things that have a different amount, a different quantity of a certain characteristic, usually price or percent. Okay, so a value mixture equation where uh, is AC equals V, where A is the amount of an ingredient, C is the cost per unit of the ingredient, and V is the value of the ingredient. So how does that differ? It really doesn't. It's still the same darn thing. It's the idea that, for instance, we got this coffee merchant with two blends of coffee into a single blend, or a candy manufacturer with combined two types of candy that sell at different prices into a variety pack. Well, the value of each of those objects, each of those types of candy or types of coffee, is going to be determined on the cost per unit, like the cost per pound for the coffee or candy, times how much we have of that thing. So it's basically just saying that when we're dealing with mixture problems, part of the equation is going to be the value of each piece, and that value is always going to be how much you have times its price. Well, when you deal with the other type where it's percentages, it's still the same idea. It's how much you have times its percentage gives you the total kind of value of that thing, but the value is now measured in how much of that thing you have. Instead of total cost, it's now, how much total alkalinity do you have? If I have 5 gallons of a mixture that's 20% alkaline, do I want to do 20% of 5? And out of those 5 gallons, 1 gallon is the alkaline stuff, and the other 4 gallons is just water or whatever, the other part of the mixture. So that's that value part that you're always going to get. So let's put it into some context. Let's use the coffee merchant. He wants to make 6 pounds of a blend of coffee, so that's the total amount that he wants. He's going to use, he's going to use 6 pounds of his $5 per pound blend. And he's going to make that by blending together some of his $7 per pound stuff and his $4 per pound coffee. So he basically wants to come up with a whole new cost point, right? He's got $7 coffee, $4 coffee. He wants to mix those two together and come up with a $5 coffee, and he wants the bag to have 6 pounds of coffee in it. So here's what you want to do with these types. You always want to make a simple table, whether it's for these cost types of things or the percentage types of things, it's always the same amount. Sorry, the same type, the same table. You've got the two things that you start with and then your total, what you end with. So in this case, we started with the $7 coffee, the $4 coffee, and we want to end with a $5 coffee. Then you're going to have 3 columns. You're going to have amount, you're going to have characteristic, and then you're going to have this value. So amount times characteristic equals value. So amount times, in this case, cost equals value. If we had percentages, when we were doing a mixture problem in chemistry or something, it would still be how much we have of each, like 1 liter of this, 2 liters of this for a 3-liter total thing. And then this is 20%, this is 30%, and we want to have 22.5% or that kind of thing, right? So it's still going to be the amount times its characteristic, either cost or percentage, and it's going to equal that kind of the total amount of stuff, the value of it. Now in this question, we don't know how much of each, right? We always have to identify the variable, and the question said, how much of each coffee do we have to add? So that's our unknown. We don't know how much we have of the $7 coffee. We do know that we want to have 6 pounds total, so we know that this amount has to be 6 minus x, because these three things always have to add, right? The first two have to sum to the third. So this plus this always has to equal that. You do not add the second column because costs don't work that way. You don't take $7 plus $4 and then your total cost is going to be 11, because for one thing, we were told that our total cost is supposed to be 5. So this column doesn't add. But the third column does. Whatever this value is plus whatever this value is has to be our total value. And that also works for percentages. So we know these add, we know these add, we know we always multiply across, right? You can see you have little multiplications here. So x times 7, there's my 7x. 6 minus x times 4, that gives me this. And then of course 6, that's how many total pounds we have, times 5, the total value of the coffee should be 30, because it's going to be 6 pounds at $5 per pound. So now all you have to do is solve for x. Well, you've got a nice little equation right here set equal to a constant that you can solve. I mean, you know that this plus this has to equal 6, but if you try to solve that, it doesn't work, because x plus 6 minus x, the x's cancel and you get 6 minus 6, you go, no duh. But this one down here, you can solve. And that's what you do. 7x plus that 4, right, the cost times its other amount, has to equal 30. Do the distribution, 24 minus 4x, this just makes it 30. Combine like terms, 3x plus 24 equals 30. Subtract 24 from both sides, 3x equals 6. Last step, divide by 3, x equals 2. And then of course 6 minus x is 6 minus 2 equals 4. So if we go back up here, we're going to have 2 pounds of the $7 coffee and 4 pounds of the $4 coffee. It's that simple, guys, right? So the table trick is a great trick for figuring out these types of things. All right, how about another one? Again, with cost. How many ounces of a metal alloy? So right there we say, hey, that's what we don't know. Ounces, that's our unknown. X is our unknown amount of ounces. So ounces, how many ounces of a metal alloy that costs $4 an ounce must be mixed with 10 ounces of an alloy that costs $6 an ounce to make a mixture that costs $4.32 an ounce. Here's my table. I've got a $4 alloy, a $6 alloy, and I know I want to end up with a $4.32 mixture. I don't know how much of this I have, but it told me I added it to 10 ounces of this one. So in the end, I'm going to have 10 plus X number of ounces. I know the cost of this, I know the cost of this, I know the total cost. I multiply across, gives me 4x, gives me 60, gives me all of this junk. And then, of course, here's my other equation. This piece plus this piece has to equal that piece. And that's what you work out. 4x plus the 60 has to equal this junk. Do the distribution, right? Here we go. Again, I would move my 4 over here instead of doing what the book does. And I would have 60 equals 43.2 plus 0.32x, right? Because if I subtract 4x from both sides, 4.32 minus 4 leaves me with 0.32. Now, subtract the 43.2 from both sides, and you get 16.8 equals 0.32x. If you don't like dealing with decimals, if these decimals are giving you a problem, well, A, use your calculator. Do 60 minus 43.2 in your calculator, get 16.8. And if you really don't want to work with decimals at all, well, remember, we can multiply both sides of an equation by any non-zero constant, and they're still equal. So you could multiply both sides of this by 10 to get rid of this one, or both sides by 100 to get rid of both, right? Because if you just move the decimal place 2 places, bing, bing, that one goes away, bing, bing, that one goes away. But we've got calculators, so we can just divide by 0.32. That's going to go away, stick it in our calculator, and we get 52.5. So we're going to need 52.5 ounces of the $4 alloy because we just solved for X, and back here, X is this many ounces, right? So we need a lot. We need 52.5 ounces of the $4 alloy added to 10 ounces of the $6 alloy to give us a total of 62.5 ounces of the $4.32 alloy. And then we can answer any question they ask, like how many total ounces of the mixture do we have? Blah, 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 blah. All right, that's it. Okay, let's take a look at the uniform motion problems and see how that technique is similar. We always know that when we're dealing with uniform motion, it's distance equals rate times time, or rate times time equals distance. The reason why we're going to write it that way is because we're going to see that we can use a very similar table, little chart thing like we did for the mixture problems. We can also use it for uniform motion problems. For instance, a car leaves a town traveling at 40 miles per hour. 2 hours later, a second car leaves the same town on the same road traveling at 60 miles per hour. In how many hours will the second car pass the first? Okay, we can do it with a table. Now, I would suggest drawing a picture. Anytime you've got uniform motion problems, it's always a good idea to draw a picture, right? We have one car that's doing 40 miles per hour, and then we have a second car that's doing 60 miles per hour. If they're going in the same direction, right, it's catching up, right? So they start at a certain distance apart. This one started over here, right, because the first car left, and then after a certain amount of time, the second car leaves. Let's say it's 3 hours later or 2 hours later or whatever. In this case, it's 2 hours later. So in 2 hours, hasn't that first car gone 80 miles? So when we start, they're a distance of 80 miles apart. Now, in 1 hour, this guy goes 40 miles, so now they're 120 miles apart, but this guy goes 60 miles, so now they're down to 60 miles. So they've gone from 680 down to 60, right? Because he's basically doing 20 miles more than this. So every hour, he gets 20 miles closer. So we now know what their actual combined rate is, and we could just do it that way with combined rates. But if we set it up into a table, we know that here's the rate. The first car has a time plus 2 because they started off 2 hours ahead of them. The second car has a time of t. Here's the distance for the first car. Here's the distance for the second car. What do we know about those two distances when the second car passes is they've traveled the same distance. So you set those two things equal to each other and solve. I like it better with a picture and then doing the combined rates, right? We talked about this in our other video about uniform motion problems, is figure out what their combined rate is. And if one car is chasing the other, it's a difference, right? So 60 minus 40, he's making up 20 miles every hour. He started, when does the second guy start? How far apart are they? Well, they're 80 miles apart because the first guy's gone for 2 hours at 40 miles per hour. So there's my distance of 80. My combined rate is 20. How long is it going to take? 4 hours. Look at that, 4 hours. That's exactly what you get the other way. By doing 40t plus 2 equals 60t and solving, you get the same answer of 4. So either way you want to do it, you get the same answer. So either figure out what your combined rate is, figure out what your starting point distance is, and then solve it that way, or use the table and set the two things equal. Either way, you'll get the right answer. They both work great. I like the table. I also like finding the combined rate. Here's our last example. 2 cars, one traveling 10 miles per hour faster than the other, start at the same time from the same point, travel in opposite directions. In 3 hours, they are 300 miles apart. Find the rate of each car. We don't know the rate of each car, but we do know that one is 10 faster than the other. So there's my R and R plus 10. We know that they traveled each for 3 hours because these guys start at the same time, not like the previous one where one car started 2 hours before the other. So we now know their distances, r times 3, and then r plus 10 times 3. And then what do we know if the total distance is 300 and they're going in opposite directions? Do we add their distances or do we subtract their distances? Well, if they go in opposite directions, right, in 1 hour, let's say one goes 20 miles, the other goes 30 miles, aren't they now 50 miles apart? So you have to add those. So you would add that. 3r plus the 3 times r plus 10 has to equal 300. Do the math. Get rid of the parentheses. Combine like terms. Isolate your variable. Simplify your variable. And there you have it, r equals 45. So the first car was going 45. When you add 10 to it, the second car was going 55. All right, so those are all of our examples, our simple examples for uniform motion and mixture problems.